Hi everyone, welcome to the Math Spellbook livestream. I'm your host Peter, and basically we are going to do some physics today. Of course, over the last time we streamed, I basically during the weekend, I basically decided to just look up some physics in addition to basically go into deeper questions about the ideas that I was studying. So currently I'm actually reading up on the definition of work. If you guys are not familiar with the concept of what work is in physics, basically it is the amount of force applied over a distance. So basically it's like force times distance. So how much of a force goes the distance? That's basically what work is. And basically over the weekend I was doing a little bit of I wouldn't say deep research, but I was basically trying to get better understanding of the concept of work, such as I was basically typing questions into ChatGPT to basically get a better idea of how can I interpret work. And I did learn some things. I did learn that basically, depending upon the mass of the object, energy also comes into play when it comes to work, such as the work energy theorem. I believe that's what it's called. Basically, depending upon the mass of the object, the energy within the mass can basically go through different masses at different types of rates, I believe. I don't know how to better phrase it, but basically what I've learned is basically energy somehow goes through different types of masses in different ways. So hopefully that wasn't confusing. So basically, let me just get on here. So I wonder if we should have the chat here. Yeah, we'll leave it here. But I will just disengage my model because it's in the way of the text. So the interesting thing is that I was reading this problem here. I was reading this yesterday actually. Two ice boats, like the one in example that was in the previous, I think in the previous chapter. The previous chapter's question, I actually looked that up. It's basically the velocity of this particular ice boat as it goes across the finish line. So basically we had to calculate the velocity of that. But this one was a pretty interesting problem because it talks about two ice boats that are the same size, but they are basically different masses. So probably they're made of different materials. One has heavier materials than the other one. And the ice boat they have basically identical sails. So they have a wind force that is actually applying to both of them. And it's a constant force, so basically it's not changing, it's just a constant force. They start from rest and they cross the finish line at distance s. Now the question is that which ice boat crosses the finish line with greater kinetic energy? So this one I thought was a very interesting one because I tried to work out, I guess so-called like the math in my head. But then I was surprised to find out that basically the solution is that the kinetic energy of both of these boats are actually the same. They're actually the same kinetic energy. Now, of course, like I began to ask, why does that make? Why is that? Like, why is that? Even though we know that mass is force is mass times acceleration. I would have thought that basically the one that had more mass would have given like more force, but then the whole point was that basically the force of the wind is doing the work, and when you think about it, it has to be a constant force here. So because it's a constant force, it's doing work. The work that it's doing upon the ships, both boats have to be the same. So basically the energy that goes into each boat, the one that has more mass, basically the energy in that boat is distributed differently than the energy distributed in this boat. The one with more mass, the one with less mass basically gets the energy much quicker. So that, when I learned that, I thought that was pretty interesting. But I think it's time to actually try to do some problems here. But I am going to do a little bit of reading too, so let's turn on the study timer here. Because I am about to read up on power, I think. I just learned this like today, actually, the spring force right here. Yeah, this problem was pretty interesting. Like the work done. I actually did try this problem myself when I was doing a problem this morning. I was surprised to find out that basically like the spring constant is like 6,000 newtons per meter, which I thought was pretty. It was pretty high, and I was like, is that number right? Is like 6,000 newtons per meter? Sheesh, that's a lot. But luckily it came out to be 3 joules, and I was like, oh, okay, that's some energy, but it's not a lot of energy. So, but I thought the spring constant was really, really strong. I was like, wow, 6,000. So let's see. Oh, I haven't gotten to this part yet. You know what? Since we're not writing anything so far, might as well just have this before us today. Let's see if we can zoom in a little bit more so you guys can see better. There we go. Ever since I've started to update my study method, I basically stopped taking notes. So basically, work energy theorem for straight line motion varying forces. Okay, so this is the work energy theorem for kinetic energy, at least, because I think for potential energy it's also the same, but we haven't gotten to that part yet. We'll probably like skim through it actually. So, oh, interesting. So acceleration, and then basically the derivative is velocity and the derivative of velocity. So from the result, the total work, the force applied, force equals ma. Okay. So it's basically the velocity in the x-axis and basically the acceleration. Oh no, it's from the velocity to the x-axis. Hmm. Let's look at this again. So it's acceleration in the x-axis, and then dvxt. So I'm guessing that these dx's cross out. Oh no, wait, hold on. No, so this is basically the velocity here, and the velocity x. So, interesting. So basically, dvx over dx over the change in x, and the change in x over time. I'm trying to better visualize this part, because it's the velocity in the x direction, but then it's the change in the velocity in the x direction. So meaning so it tells us that the total net force F is the total work. So this is acceleration, and then basically we have, so now dv dx, so these cross out, and it's the change in velocity of x during the displacement of x, so it becomes this. So it's the change in the velocity with the, oh, okay, so it's just showing you the way of interpreting the work energy theorem. So basically, I'm guessing this is supposed to be like for more curve paths. Because this is the change in V1, V2. Yeah, so if you integrate it, then there's, oh, okay. I kind of made that more complicated than it should be. Okay, so let's just shrink this back. Okay. Oh, we have a problem here. So let's actually see if we can solve this problem, because that's what I've been trying to do with like reading this physics book actually. So let's see, an air track glider. So we'll have a mass of 1 kilograms. Okay, cool. We don't have to convert units with that. Cool. Is attached to the end of a horizontal air track by a spring. So we have a spring with a constant force. So that's a K because it's a spring. Newtons per meter. Initially the spring is unstretched and the glider is moving to the right. Okay, so we have a velocity here. Thinking that's initial. Okay, so the question is find maximum distance d that the glider moves to the right. If the air track is turned on, so there is no be if the air track if the air is turned off so that there is kinetic friction with a coefficient K. Okay. Alright, so I think we're going to minimize this, and then we're going to expand this. So that way we're not tempted to look at the answer. So alright. So we have a mass of 100 kilograms, and we have a spring constant of, so the force of a spring, actually how did that problem describe things? I want to draw it so that way I can have a better visual. Let's see. An air track glider with a mass of is attached to the end of a horizontal track by a spring with a constant force. For some reason I'm thinking of a hang glider, but that probably isn't what they're talking about here. We'll just make a triangle for the glider, because I can't think of anything else than a hang glider at this point. And what else is in it? By a spring. We'll just make the spring like that, I guess. And this one has a mass of kilograms. And then the force is K. So what did the events talk about in the question? Initially the spring is unstretched and the glider is moving at find the maximum distance that the glider moves to the right. If the air track is on, so there is no friction. So I'm guessing the spring is underneath the air glider, so maybe we have to draw this differently. So I'm guessing it's sort of like this, and then we have this spring here. Let's see, attached to the end of a horizontal air track by a spring with the force constant of initially the spring is unstretched and Is the spring... I feel like the spring is supposed to be horizontal then. The way they describe it. Okay. So you have to find the maximum distance d that the glider moves to the right. And when does it gain velocity? Initially the spring is unstressed and the glider is moving to the right. Find the maximum distance that the glider moves to the right. If the air track is turned on so that there's no friction, and if it's off. So I'm thinking air is supposed to be blowing from here, so we'll just label that air. So we have the spring force. We just don't know the distance here. So if the air track is turned on, then there's no friction, so means so we only have the constant, but we don't have like the distance, and we don't know the force. Unless I'm reading this wrong. Let's see, by a spring with the constant force of force constant. Well, force is usually per meter. So that means that is the spring constant. Okay, I wanted to make sure the units are right, because if it was force, then it would be newtons, not newtons per meter. We also know that the work total is the difference between the kinetic energy. So. And we're not dealing with friction here, so friction's not gonna... Well, in the first part, we're not dealing with friction. So... we do have the mass and we do have the velocity. And let's assume that basically, so would this be the final velocity, or would it be the initial? Like, I keep rereading the question over because I feel like I'm not getting all the details. Because it says initially the spring is unstressed and the glider is moving at 1.5 meters per second. So that's why I think it's in the initial velocity. So that means the final velocity, I'm guessing it would be 0, because like they don't really give you details about that. So does that mean it's doing negative work then? Because so if we know work is distance, and let's just say we're dealing with, let's just put V here. So meaning, so that means we're dealing with, but we don't know the force though. Because all we know is the spring constant. missing some pieces. That's the thing that's kind of annoying. But I guess it's up to us to find out what those pieces are. So the spring is not... and we don't have time either. So maybe... let's see, final velocity. But we don't know acceleration. But I don't think it's changing, so if we, then that would be 0, and the final velocity will equal the final velocity. The initial velocity will equal the final velocity. Okay, so we got the mass, we got the constant. We just don't know the acceleration or the x. So, how could we do this? I feel like it's there. It's just that we're missing so many numbers or variables, I should say. Maybe we don't really need this. What's confusing me is that I don't know if we have all the equations we need. Because we need an equation that actually is something... because we don't have the force, that's the problem. We do have a constant, we do have a spring constant, but we don't have the actual force it does. And we don't know what x is. Yeah, I'm stumped. But what is the solution here? So if the force exerted on the spring is not constant, so we cannot use the constant acceleration formula of chapter 2. Well, actually, I should make this bigger for you guys so we can actually see it. So let's see. So we cannot use the constant acceleration. I'll make it a little bit bigger. There we go. I think that's better. Formula to solve the problem. Instead, we use the work energy theorem. Okay. Since the total work done involves the distance, our target variable. Oh, that's what it's supposed to look like. So let's see. We choose the positive x direction to be the right in the direction of the glider's motion. We take x is equal to 0 at the glider's initial position, okay? Where the spring is unstretched and x is equal to d. The target is at the position where the glider stops. The motion is purely horizontal, so the horizontal force do work. Note that equation 6... where is that? This one. Hold on. expect the glider to move further without friction than with friction. So, okay, so we're given a hint here. So let's try that actually. Where is it? There it is. So the formula we have is, I think it's the total work done is x2. I think right now we can just do it's d, and then kx. Which equates to so that's the total work done. Now does that kind of helps us a bit. So that's the total work. Meaning so if we're given that, that is the total work done, then the kinetic energy us, but we'll give it a try here. And I think I almost forgot we should have our trusty calculator on us. I always remember to bring my calculator in here, but I always forget to put it up for you guys, so let's just shrink it a little bit. There we go. Alright, so that gets us the variables we need. So hopefully so the mass we have here is 0.1 times oh no, we need the velocity. Oops. Almost typed in the wrong number. And that divided by K. So K is 20. Yeah, 20 newtons. Divided by 20 newtons, close parentheses. So that leaves us with a distance of 0.1 meters. And that's without friction. So if the air is turned off, so there is kinetic friction with the constant, with the coefficient. Okay, so I think that would be Because with friction, because I know like it would be the object's weight. So let's label this for A, and then we'll just do that. Now we gotta figure out what B is. So if air is turned off so that there is kinetic friction with the coefficient. So for a force with friction, it would be the object's weight minus the friction. And I think you would have to multiply the coefficient of friction with the weight. I believe that's how it's done, I think. Let's just do a quick calculation to see if that makes sense. Oops. I meant this calculator, not my computer one. So we have a mass of around 0.0 kilograms. And then you multiply that by 9.81. And then minus that by the amount of friction. Times. And then multiply that by so we're left with a force of like 51. And if the air is turned on, the kinetic friction so we still have to calculate for D, but this time we're gonna have to do it where the air is turned off and there's a kinetic friction here. So we can do that by basically using the equation that we had before. At least I think so, because now we have a force that we can work with. I think the force that we have, I could have calculated all the forces wrong, so this will probably be better. So put 0.52 newtons. So that's the total force with with friction. Because I'm pretty sure that's what the force of friction would be. I think. I haven't worked with friction in so long, actually. Okay, so... Alright, so I think we just have to put the numbers in. Here we are. So we'll clear this, and then we'll type in the mass is 1... Oops, forgot the decimal point. And then multiply that by the velocity, which is squared. And all of that is over 2 times What's the answer in here? Leaving us with a distance of 0. What was it, 2? 2 something? 22. We'll just put 0.22 meters. Okay, so without friction it goes a little bit less, and yet it goes further with friction? I don't know. That doesn't seem quite right. What am I missing here? I'm missing something. Because it says, wait, so the air's turned off, and then, so there's no friction, so it goes 11. Huh. But yet it goes further with this one, which doesn't make sense. I think I did something wrong with the force calculation here. Let's see if we got the first part right. Nope. I mean, did we set it up right though? Yeah, it seems like we set it up right. Let's see. Yeah, K is on the bottoms, and yeah, so the setup is right. Maybe we just put the wrong numbers. Let's see. Maybe I put the numbers in the wrong places. That could also happen. I mean, we did set it up right, so let's take our calculator out and see if we can calculate again. Maybe I put the numbers in wrong. So I guess we'll do it the way they set it up. So the velocity is and then the square root would be the mass over 20. So 0. And what did the books showed? Oh, they did it in centimeters. That's why. Okay, so we did get that right. Okay. So let's see the work on friction. Let's see, friction is. Oh, we did write friction correctly here. So the total work sum of friction work done on the spring. So what did they do here? Let's see, so cosine of 100 AJ is force of friction. So at least I got the parts of friction correctly a little bit, but they also added D in there, which is because it's supposed to represent work. And D times distance. Oh, so they turned it into a quadratic. So we didn't get part B right, but we got part A right. So what did we learn from here? So basically they turned work. So from my understanding, they basically just turned the work value theorem into a quadratic equation. Yeah, which makes sense because like basically they're just turning the work into because I just used force. I didn't really incorporate like this formation. Kinetic friction. I mean, do you have to actually do all that? Let me take a look at what I did. Because we did get the force here. Because I just took the force and I just basically just like rearranged things. I mean, that's not the correct answer according to that though. But then maybe that's why I got the funny answer. So we couldn't use this. So according to them, so they basically used the definition of work here, and then basically turned so this would be like the total work done without friction, but then we have the minus friction, so mg so that's the total work done, and I'm guessing by using the theorem here, which is equal to less, because this is the initial velocity. I mean, at least I've developed a sense where it's like, oh, with B, I thought something was funny. Because, yeah, the numbers didn't look like they were right. Because it's like with friction, you're supposed to have less distance, not more. Which I thought was pretty weird. So then they turn it into a quadratic. Like this. Then the square root of this squared minus 4 times k over 2 and that is over k. I mean, that looks like a crazy equation. So then the way they calculate it, so this is going to be a doozy. So calculate that. the mass of times this minus... Nope, that's not what I want. That and minus 4 times, I think that would be like 10 newtons. Make it a little bit easier. And then the mass is type outs here. I think we have to put another parentheses. At least, like, my calculator, I can't, like, go back to, like, what I was typing. Oh, let's see. Or maybe we have to do this. Oh, whoops, I almost forgot. Because since there is a... this becomes 2. We can leave this at 20. Well, it's break time. Hopefully you guys are having a decent start to your week so far. Yep. Yeah, I think like I learn a lot more when I actually go over these like problems in the book and I try to do them on my own. And then like basically when there's like time to actually go to the end of the book and actually see the problems in there, that's when I'm like, okay, now I gotta actually like see what I have to foresee. But this one was an interesting problem, actually. At least we got this part. Like this part, I'm actually glad we got it. Like we saw like a partial hint right here. So I'm like, okay, this makes it easier. Which is good to know because then I'd be like, okay, I gotta remember that we can use this. But depending upon the context of what we're dealing with here, I guess the calculus part kind of made it easier. But anyway, if you guys are in the chat, and even if you're lurking, it's okay to be lurking. But if you like math, physics, or just a productive stream to keep you guys productive in whatever it is you're doing, drop me a follow if you can. That is if you want to, of course. Because the thing of it is that like whenever I basically stream on this channel. It makes me feel as if like, wow, we're actually like reaching people that love math or love physics, or you know, just basically just want to be productive and doing the things that they find awesome. And you know, that's the thing that I think is like the most fun, is like being able to help people get to the best part of their lives, even though it's the most hard. Like, you know, like if you got that drawing or art project you have to do but you just want to procrastinate, it's like, you know, be empowering. What did they show in the book actually? So what we gotta remember is that we can use like basically the quadratics to basically make it this way. Yeah, because the way it looks like it's like less of a distance, which it should be. Yeah, because this should be like this should be less, not more. Because the way we calculated was like kind of weird. I was like, why is it like more? It shouldn't be more. It should be less. Oh, the next one is going to be interesting. The work value theorem under a curve. That's going to be fun. Adding more calculus to the whole thing. I always keep coming back to this book, University Physics with Modern Physics by Young and Friedman. I don't know why. It's just that I think I just like the way this book is made. Like they basically put the blocks around the important equations and stuff, but I think the way they explain the problems are a bit it's easy for me to understand. At the same time, I just wish that there wasn't so many problems that makes me feel intimidated. I mean, it's good that you can do a lot of problems in this book. The thing of it is that like sometimes like I think like when textbooks put too many problems in a book, it makes you feel intimidated because you feel like you have to practice all of them. But in actuality, like I remember watching a YouTube video of I think someone who did their master's in physics, and they basically said in their study tips video that what they would do is that they would like do a problem from each section, and then they would come back to it every time they'd study. So basically they would do a problem from this section and do a problem in the next section and do a problem in this section and do a problem in that section, which I think is much easier to do because like it doesn't make you feel like you're overwhelmed that much. I mean, like just doing one section alone, like little by little, like I think that's also helpful, because like for me, I've learned a lot about work and I still don't know everything about the work energy theorem, but I'm starting to learn more about what work does and how does that relate to energy. And I think when you learn like the little tiny bits of it, you can just go on like AI tools like, you know, ChatGPT or other AI tools that you guys might find more useful, and then type in your questions into the AI, and like sometimes the AI is not like 100% accurate, but it can help lead your thoughts to, I think, a better connection within your mind to find exactly what is it that this physical idea encapsulates. Because I think over the weekend when I was like talking with ChatGPT about like I guess my struggle with physics, and you know, because like I really love this subject, but at the same time I know I'm very, very bad at it. And you know, like I went through like I guess like a lot of people that love physics and mathematics will probably understand. It's like you love the subject, but you know you're not very good at both subjects, and you're like, why am I so bad at it, but yet I really like it? And then it's all about just basically finding the right support. Because like I think with ChatGPT, I was getting frustrated by the fact that I was getting Fermi problems completely off by like a magnitude. Like basically like I was getting them over a certain order of magnitude. And then basically ChatGPT basically like, you know, gave a little bit of a pep talk with me. Basically saying like, you know, like when you do Fermi problems, it's not meant to be correct. It's just meant to be a system you develop to basically get things in the ballpark. Like, I think ChatGPT gave me a problem. Like, I think it's a classic one. It's like, calculate how many piano tuners are in the city of New York. And, you know, for me, I actually just assumed, because I don't know the population that lives in New York, so I assumed that the population was like around 100,000, which was way off. And basically, I was like, okay, so how many homes would have a piano? And basically, I thought about like a family of 5 or 4, and I would divide that from the population. And then once that happened, I basically thought, okay, so how many pianos need a tuner? And basically, I thought like every 3 pianos there would be 1 piano tuner. So yeah, and basically, like, I put my results, my thought process and my results in with ChatGPT, and basically ChatGPT was like, okay, that's a really good system you developed to basically come up with the solution. And then it provided me with like its own way of doing a Fermi problem. It actually took the data of like how many people are in New York, and then basically like did almost the same thing I did, but it added another thing, which is basically like how many times a person needs to tune their piano, or how many times a year a person would need to tune a piano. But I think that was just an extra detail it added, so it didn't feel like it was really needed. I mean, and the thing of it is that like the point is that thinking like a scientist is on a different wavelength than thinking like a mathematician. And I think like what was kind of holding me back with physics was basically like being able to think like a scientist instead of thinking like a theoretical scientist. Because I think I tried to rush into like thinking like a mathematician slash physicist, like thinking like the math will lead me to the physics, when in actuality I have to let the physics lead me to the mathematics. So, you know, I think that's what with physics you have to deal with, and I think that's what mathematicians are not used to, or at least people that are mostly math majors are not used to, is that they're not used to actually detaching from the math. And I think that's the thing that I was struggling with, was I thought that the math would lead me to the physical answers, when in actuality you have to let the physics lead you to the mathematical formulation, and that's hard to do. But at the same time, it also kind of allows you to actually think about what is it that you need to do to actually make the math appear, which kind of feels like magic. Hence why I call it the channel Math Spellbook. You know? So I think that's how it be. Like I think when you start learning physics, you have to learn, like, especially if you love math, you have to learn to turn off your brain and you turn off your math brain and let the physics do the talking. Hey Bamboo, how's it going? What's the best part of your day so far, my friend? Yeah, we're basically just trying to learn more about work and energy. Oh, nice. An interview for what exactly? Is it for a job, or is it for Oh, nice. With Harvard and Caltech. Ooh, nice. Nice. Congratulations. Like, what is so basically you're going for your PhD there, right? Or like you're basically just being interviewed for that, right? I'm jumping around like a kangaroo. I'm happy for you. That's great. Harvard and Caltech is nothing to scuff about. That's really, really good. Congratulations. I'm so happy for you. What do you plan to do research on for your PhD there? Astrophysics? Okay, that's cool. Do you have any idea of what you're going to research on in astrophysics? Like asteroids? Are you going to research like exoplanets, dark matter, dark energy? Well, what do you plan to research? Or any of the moons? You plan to do research on the moons or anything? Dark matter, dark energy, the CMB radiation. Oh, that's nice. So would that be in kind of relation with cosmology? Are you like going deeper into like a little bit of the cosmology track? Or is that just mainly you just want to focus on like one of those? I already released 2 research papers. Oh, I would like to read those. That is indeed cosmology. Oh, okay, cool. So you're already ahead of me when it comes to that. I wish I was at your level then. But I still have to know the basics because I'm still learning about the work energy theorem. I mean, I am getting a little bit better, I think, but at the same time, I still have to like work on a few things. But that's cool that you're actually getting to be interviewed for like Caltech and Harvard. Those are really big deals. Okay. So I feel like that. I feel like that about matrix and determinant sometimes. Like, what do you mean? I mean, we learn all that like within algebra and linear algebra, so is it because of the calculation involved? Is that why you feel that way? Yeah, like what I was saying before is that basically I have to learn to turn off the mathematics in my brain when I'm doing physics problems. I have to learn to actually let the physics tell me what the math is going to be. And I think that's the thing that I kind of learned over the weekend about physics. I want to be able to think like a theoretical physicist, but at the same time it's like I have to know that I'm not at that level yet, so I can't think of things both mathematically and physically. Let's see, matrix formalism in the CMB radiation polarization analysis. Oh, okay. Trust me, I'm still going crazy over this. Oh, okay. Well, you're going for the research, so at least you'll be able to do it as a, like, you know, a career path for you. Me, I'm just doing physics as a hobby. I mean, it would be nice to actually basically make a living off of this. I'm basically just making a living just studying and doing the same things. Well, not the same things, of course not, because you're doing it as a career. For me, I'm just doing it as a hobby. And of course, like, you know, like people that do like studying as a hobby, like, you know, they're like, it would be advantageous or like even egotistical to say that, oh, when we do it as a hobby, it's the same as you guys doing research. It's like, no. You guys have more access and you guys know how to actually set it up so that a whole audience within your own peers can understand. I'm going to go insane in a year or two. Hopefully not. Like, you know, just maintain your health, I think. Even when you're going for your PhD, I think just maintaining your health is the important thing. I know you're doing it to get future prospects in your career and your PhD, but don't forget to like live life, you know, like, you know, like take a lot, make sure you rest, make sure you don't lose the inspiration by just basically saying, oh, I'm doing the work, but at the same time you kind of feel as if like this work is going to be the end of me. Like when you lose your inspiration, just try to find it. Like sometimes that's the time to actually step away from the problem. Sleep schedule is pretty, yeah, I get that, but at the same time, like I think that's the thing that PhD students have to actually like learn to adapt to. It's like, I'm not saying adapt to less sleep, I'm just basically saying they have to find a way to make a sleep schedule that works for their body so it doesn't break down while they're doing their research. Because I feel bad for PhD students because they always put their bodies in the most harshest conditions because they know they're working hard towards something that means like an extension of truth, even though they know they're not going to get wealth from it. Not that that's a bad thing. I actually respect people that do that. I think I remember telling you about giving GIS and GATE. My GATE results came out. I'm waiting for oh, what are those again? Are those like exam results or research results? You're gonna have to remind me what the gate and the gist is. But before I get to that, I will be right back, guys. Just give me one quick second. Okay guys, I'm back. Sorry to keep you guys waiting. Joint entrance screening test, graduate aptitude test in engineering. Oh, okay. So why'd you have to take those exams again? Both are national tests, okay. They add to my profile, so it's good. Oh, okay. I see. So that means you have more experience. I guess like it shows that you have the aptitude to be, you know, whether it be an engineer, like in case you don't want to work in academia, as well as if you want to work in, if you want to do particle physics. I'm guessing, you know, it would be good to show that you have that on your CV or resume. But that's good. Like for example, I got all India ranked top 50 in gate. Oh, okay, cool. That's good. That's really good, actually. Yeah, you're way smarter than me then. But that's great. Congratulations. I hope your GIST scores are just as exceptional. I mean, like if you work in say like CERN or something, they basically like, oh, you got like a good score on your gate here. So does that mean you can help us extend the Large Hadron Collider? Or like know what's wrong with it or something? I mean, that is if you want to get into particle physics. I mean, with cosmology, it's practically a given you have to learn about quantum mechanics to some degree. Especially with quantum field theory. Both exams help in a lot in general, except US. Why is that? Is it because the US standards are much higher? Yeah, come to think of it, like, I feel bad for people that actually get, like, higher degrees in other countries, but then when they go to another country, whether it be, like, Europe or the US, it's like, it feels as if, like, oh, you didn't get a US education or you didn't get a UK education, so obviously you can't work in the field that you actually studied for, like, a majority of your life in. Which I think is really BS. US thinks that they're better than everyone else. I don't doubt you there. Anyway, let's get back into our second study session. So now we're reading about the work energy theorem for motion along a curve. Okay, this one is going to be pretty interesting. Okay, so let's see. So like, let's see. Figure 6.23. Oh, okay. So now we're gonna have to do calculus with this. Okay, thanks for chilling with me for a while, Bamboo. I wish you luck in your future prospects. Keep me updated. I remember this theorem. It's subparts word to word. Yeah, take care, Bamboo. Take care. Good luck. Good luck. Okay, so where are we? Oh yeah, here we go. Okay, we can generalize our definition of work further to include a force that varies in direction, as well as in magnitude, and a displacement that lies along the curved path. Okay. Shows that the particle from P1 to P2. So we got P1 and P2. Divide the curve in between these points. So many, yeah. Okay, so typically it's like the derivative. Oh, I forgot to turn off my model. I don't want it to be popping in and out whenever like I look down at my tablet. Okay, so back to studying here. Okay, we divide into, okay, so basically dl will be the little derivative points there. Is tangent to the path, okay. Be the angle, okay, so that's the angle between the force, okay. Component in the direction is parallel to dl. Okay, so this would be like the hypotenuse, and this would be like the adjacent. Okay, I was like, why does it have to be like so it's the dot product, excuse me, sorry, so it has to be the dot product of the force and the vector dl. Okay. Oh, we actually got a problem straight up. Nice. Okay, so let's see what this one is. The component of so we have to remember that it is the cosine, the force of the cosine, and okay. So let's minimize this, and then we can open this up again. We'll minimize that. Put this down here. This down here. Okay, at a family picnic, you've been appointed to push and it's just cousin on a swing. Okay. Until the chains make an angle. Okay, so we could probably draw the picture because the picture is right next to it. So we'll just put a string here. Then we'll make a little stick figure of a kid on the swing, like that. Not the best artist. Put a little bit of a dotted line there. And a little force here. And DL right here. Oh, that looks like a towel. DL. Like this. And we have a length of R here. Okay, his weight is, let's see, his weight is W, so this is the weight. The length of the chain is R, and you push the hockey until the chains make an angle theta. Okay, so basically it's just a formulation problem. To do this, you exert a force horizontal that starts at 0 and gradually increases enough. What is the total work done? Okay, so the question is, what is total work done on by all forces, and what is the work done by the tension T in the chain What is the wow? We have to do a lot of what is the work? What is the work you do by exerting the force F? Neglecting the weight of the chain and the seat. Okay. Okay, so we've written everything. Let's just extend that right here. Okay, so what is the work? What is the total work done on by all forces? So, didn't mean to do that. Okay. Well, now I gotta bring it up. Okay. Now. So what we got is cosine of theta. And what was the DL? This is supposed to be like the vector DL. Okay, so what is the total work done by all forces? So R is the length of the swing. What is the work done by the tension T in the chain? So actually, let's just write A here and then B here, so that way we can keep these organized. What is the work you do by exerting the force F? So first we gotta do the work that our cousin, the kid, on the swing. So that would have to meaning A open this. I meant to open this. Okay, the length of the chain. So we gotta remember what tension is. So tension is basically the tension is equal to the weight, hence it's equal to negative mg because it's going down. And it is also a pendulum, so does that mean we also have to multiply it with the length? No, I think the length is going to have to be in conjunction with the angle at some point. Because I think the force... Yeah, because now I gotta remember the formula for a pendulum. Let's see, identify and set up the motion along a curve. So we'll use equation. Yeah, we'll use that equation to calculate the work done by a net force by the tension force and by the force F. So this is the tension. T of cosine. We replace the sum of the tensions in the two chains with a single tension. So I guess we'll just draw the same graph they did. And so the force is going this way. And so this is the tension. This part, this is T cosine. This is sine here. Okay. So in this case, so does this mean it's the only force that kid does is the tension plus going so do we also have to add the force from our push? No, I don't think so. So does that mean it would be t to the cosine L? Because the boy doesn't, or the kid doesn't have, only applies the force of their weight in addition to, I guess, like with the swing, they're applying like somewhat of a pivot, like somewhat of a pivot with their body to basically push the swing higher, which is probably similar to like DL in this case. Yeah, DL. So I think that would be the work done in this case for A, at least. Or in this case, it would probably be like D, tension, the dot product of DL, somewhere around there, I think. So, okay, so what is the work done by the tension in the chain? I mean, the tension in the chain is just going downwards. It's not really like, well, actually, if the tension in DL, the change in DL, I mean, they're not perpendicular, but they're almost close to being perpendicular. I think the work done on the chain is just basically the tension. Because actually, we have to think about R here in this case. So like the work done by the tension, we'll put a little T there. Tension done by the kid, right there. Okay. So the work done by the tension in the chain. So I think it's going to be the same behavior as like if you do with the pendulum. Now the thing of it is that I forgot what the equations of a pendulum do, or how to write those. So we know that R is going to play a part. So we'll put R in there. So that's the length of the chain, and the tension is basically the thing that keeps R lengthened. So R is basically the maximum of what the tension could be. And then basically the angle because the tension in the chain of the swing, basically it will never get to R unless it goes back to its original position. So times r in this case? Well, no, because r is basically the full length of t. Well, actually, let's just check out the first part of the question. Let's see, there are two ways to find the total work done during the motion. One, by calculating the work done by each force and then adding those quantities together. And two, by calculating the force done by the net force. The second approach is far easier here because it's an equilibrium at every point. Hence, the net force on him is 0. The integral of the net force is 0. The total work done on him is 0. Well, we didn't get 0. We just wrote like a bunch of scribbles. All right, so he's not doing any work. Oh yeah, because work doesn't work in a horizontal, vertical, on a vertical direction. I forgot about that. I should have remembered that. Which shows that I have a lot of work to do to understand these things. Okay. Okay. It's also easy to find the work done by the tension in the chain, because this force is perpendicular to the direction of motion at all points along the path. Hence, at all. So if it's not vertical, does that mean the tension is also not doing any work? Hence, at all points, the angle between the chain and the displacement vector is 90 degrees, so it's also 0, right? Okay. Thus, the chain tension does 0 work. Okay. To compute the work done... Actually, I should have just made this bigger. Okay, to compute the work done by F, we need to know how this force varies with angle theta minus the tension sine equals 0. By eliminating t from these two equations, we obtain the magnitude F is equal to the weight tangent theta. The point where F is applied move through the arc S. The arc length S equals the radius of a circular path multiplied by the length theta in radians. Okay. Therefore, the displacement dl corresponds to the small change of the angle d theta. Has a magnitude of so the work done now we express that F is weight and one minus cosine. If there's no displacement, if equal to 1, then the work is 0, as we expect. If theta is 90 degrees, and then cosine equals 0. Hence the work would be, in that case, the work you do is the same as if you had lifted straight up the distance r with the force equal to his weight. In fact, as you may wish to confirm, the quantity r is the increase in his height above the ground during the displacement. Well, that was a pretty big mouthful to like read out. Oh, now we're getting into power. The difference of work over time. So the derivative, so power is the derivative of work. Interesting. And it's measured in watts. That's easy to remember. Let's see, power is the time rate at which work is done. Like work and energy, power is a scalar quantity. Okay. Instantaneous rate at which work, which force F does work on a particle. Oh, okay. So it's force, the dot product of velocity. Okay, we're given a problem. Let's try this one. Okay. Let's just shrink this. Oops. Didn't mean to write that out. What's up here? Okay. Each of the 4 jet engines on an Airbus A380 airliner develops thrust, a forward force on the airliner of... So we got a force, which is roughly pounds. Wow, that's a lot. When an airplane flying at velocity of 250 meters per second, which is roughly 900 kilometers per hour, or well, actually, or 5 miles per hour. What horsepower does the engine develop? Oh, man, I gotta convert it. Okay, so P is equal to the dot product of perpendicular to each other. So that means that they have to be. So we assume that cosine is going to be equal to 0 in this case. And then plus the velocity, which is 250 cosine of 0 degrees. So the power in this case, if we bring out our trusty calculator, I mean, it's just basically just adding these two up. Although I don't know how to convert that to horsepower though. Okay. Oh wait, what the heck? Oh yeah, that's right, I forgot. Why'd I add them? It's supposed to be multiplied together because they're both x coordinates. It happens. Like my brain is like basically like going many areas at once. So it is like 8.5 times, let's see, 1, 2, 3, 4, 5, 6, 7. To convert that to horsepower. So that would be, oh, it's 746 watts. That's not going to be easy to remember. Yeah, I have to remember that. Like, I thought of dot product and I thought about the addition part, but I forgot about the coordinates, the components multiplied to each other. I guess it's because I'm so used to like things being separated by sections, but then I forget that, oh wait, we have to put them all together. Oh, here's another one. So let's just drag this up here. So we have a mass of, for a runner running upstairs, and the height, meters. So the time, 15 minutes. So let's just convert that. So 1 minute is equal to 60 seconds. So 15 minutes times 60 seconds, around 900 seconds. Okay, so the question is, what must be her average Express your answer in watts, kilowatts, and horsepower. Okay. So we're given a distance, we're given a mass, and we're given a time. So we have to figure out what her output is. So in 900 seconds. So we're given a distance, so that way we can get velocity. There we go. Oh. That's not what I want to do. Why is it doing that? Let me refresh this. I was like, that's not what I wanted to do. Alright. 900 seconds. Why is it just giving me a fraction? Wow. Alright, so I wanted the decimal version of it. Per second. Okay. Okay, so we're given the velocity. But we don't have a force, so we have to figure out what force we're dealing with. What must her average power output? So I'm guessing we're gonna have to do the same thing here, but this time we're gonna get the acceleration. So if we're doing this for given 5.4 meters per second squared. Is that even right? Then the power is going to be the force. So then we're given mass times, but she's going up though. Maybe acceleration should be gravity. Because that's what's the force that's pushing her down, but she's going up. Or at least the x-coordinate. Because it is the dot product after all, so in this case we don't have an angle though. I was about to write cosine of theta, but I'm like, no, that doesn't seem right. Oh. That's... I forgot that power is supposed to be work over time. Dang. Yeah, because the last question was basically about force and velocity. So basically, I have to remember that there's like different types of questions. So the work done. And then we get the work done over that. Oh, okay. Yeah, I guess like doing a lot of problems like I still have to train myself to do a lot of problems for a long amount of time, especially when I'm streaming with you guys. But I think that's about it for today. We did learn a lot about work today. I mean, it was me just looking over problems and trying to solve them on my own. But like I said, like on these streams, guys, you guys will see me fail a lot. That's what happens with math and physics. You're gonna have to face failure like more times than you care to admit. But at least I learned a little bit more about work, and hopefully you guys did too. Anyway, if you're watching this on YouTube, you know, be sure to drop a like and drop a comment down below, and you know, like hit the subscribe button if you can. And if you're watching this on Twitch, whether you're lurking or you know, if you like math, physics, or you just need a productive stream to basically keep you occupied, you know, drop me a follow. And if you would like to sub, you're more than happy to do that too. For my Twitch chat, I will put up my YouTube channel so you guys can subscribe to that if you want to see what we did at the beginning of the stream, if you missed some parts of it. And I will also put the Discord in the chat as well, in addition to my Uncle Talks video game channel. I will be streaming on that channel today as well, so you guys are more than happy to check out the video games that I play there. And if you're watching this on YouTube, all of the links will be in the description down below. So thank you guys for joining me today. I will see you guys tomorrow. And always remember, everyone is precious. You guys are just as precious as everyone else. And I will see you guys in the next stream. So take care, guys. Bye-bye.